Alright, we're going to go ahead and finish off section 10.5 here with one final example. Let's go ahead and jump right in. The costs of 30-second ad slots during the Super Bowl have increased greatly, even when adjusted for inflation. Let C be the cost in millions of dollars of a 30-second ad slot at T years since 1960. And then they've given us some data here. They've given us the Super Bowl number in Roman numerals, the year that Super Bowl was played, and then how much it costs to run a 30-second ad. So $0.3 million back in 1971, so $0.3 million would be $300,000, and in 2009 it was $3 million. And they're going to want us to do some modeling on this. They're asking us to do linear regression, quadratic regression, and exponential regression. And I will show you how to do all three of those, but to be honest with you, if it was up to me, I would just graph this data, and without doing all three, I would look at the shape of the data to see which of the three was appropriate. So let me go ahead and show you that, even though they're not asking for it here. So for the year, I don't want to have these be my inputs. I need T, which is the number of years since 1960. So I'm going to make a T column where I subtract 1960 from all these. So 1971 minus 1960 would be 11 years. And 16, 21, and so on. In 2000, subtract away 1960, you get 40 years. 2006 minus 46, and then finally 2009 minus 1960 would be 49. So those are my values of T, and those are going to be my inputs. So when I go to the graphing calculator, I'll put those in L1, and then these costs are going to be my output, so I'm going to let that be L2. And I'm going to go ahead and enter that in, and we're going to take a look at the shape of the scatter plot on this. So let me go ahead and do that process. So I'm going to hit Stat and Edit, and enter those values of T into L1. And then I'm going to move over and enter those costs into L2. And then I want to take a look at what that shape is like. So I want to think about the window. For my X window, I'm going from 11 to 49. I think I'll just go from 0 to 55, and I'll probably use a scale of 5s. And here for my Y values, I'm going from pretty low up to 3, so I think I'll go from like 0 to 3.5 and use a scale of 0.5 for that one. So let me set up that window. So the window would go from 0 to 55 with a scale of 5s, and for the Y values from 0 to 3.5, and I'll number it in halves. So let's take a look at what that scatter plot looks like. My plot is not turned on, so let me hit the Y equals key. You can see my plot was not highlighted, so I'll highlight that and press enter, and then that plot should be ready to go. So let me try that again. Alright, so here's our scatter plot. Looks like it's curving a little bit. I've got one kind of surprise number right here. Seems a little bit high, so that makes me want to double check my data, but I see it did go from 1 to 1.2, all of a sudden it was a jump to 2.0, so that probably does make sense. And then they want me to think about, should I do linear, quadratic, or exponential? So frankly, I would just make that decision right here instead of doing all three, but they're asking for all three, so I'm going to show you how to do it. But when I look at this, this is kind of a curving pattern, and so I think that linear isn't the best bet. With quadratic, if you have curving, it'll rebound and start curving up on the other side, and I don't think that necessarily makes much sense here for ad revenue, like it used to be high and then it went down to almost nothing and then it started going up. Steady growth makes more sense, and this is curving, so steady curving growth is exponential. So I think exponential is going to be the best bet, but let me go ahead and show you how to do all three. And then since they're going to want me to graph them, I'm going to show you how to store those as well. So I'm going to go ahead and hit Stat and Calc, and I'll do the linear regression first. So I'm going to highlight linear regression AX plus B. I'm going to tell it where my variables are. So L1, comma L2 is where I put the variables. And if I want to store it, then I want to store it in Y1, so I'm going to use the variables key to get at that. After the L2 I need a comma, so I'll put that in. Then I'll hit the variables key. I want to go to the Y variables, so I use the arrow for that. The Y equals our function, so with that function highlighted I'll press enter. and I want to store that in y1. So this will give me the linear regression just like always, but it'll also store the equation in y1. So there's my slope and my intercept, and if I hit the y equals key, it's also stored in there and ready to go for the graph. So we'll come back to that later. Let's do our other regressions as well, and then we'll write them all down afterwards. For quadratic regression, I'm going to go over to Calc again, Stat and Calc, and this time I'll choose quadratic. Again, tell it where my variables are, L1 and L2. And then I also want to store it again, so I'm going to hit variables, y variables, function variables, and this time I'll store it into y2. I don't want to choose y1 again, or it's going to just get rid of the one I did for the linear. So I press enter, and it tells me what the a, b, and c are for the coefficients of my input squared, my input, and my constant. And if I hit y equals, now I've got that function listed there as well. And then finally, let's go to Stat and Calc, and they want the exponential one, so I'll go down to exponential regression, tell it the variables, L1 and L2, and then store it, variables, y variables, function, and I'll put this one in L3. So that gives me my coefficient and my base, and again, also stored, you can't see it, but if I arrow down, we'll see that stored in y3. So they wanted us to find all three of those, so let me go ahead and write those down. Looking at this menu, I can see all of them. The first one, it's linear, so they want us to use a function called L, and then the input is t, so I'm going to say L of t equals. But I just want to do mx plus b type of formatting, or in this case, really, since the input is t, mt plus b. So I don't think we want to put like 14 decimals or whatever they have here, so I'm going to go ahead and put 3 for all decimals I see. So for y1, I'll put the linear function is 0.069 times t, then we have plus a minus, so I just write a minus sign, 0.838. Now it does actually say 7, but followed by an 8, so I'll round that up. So that's my linear function. With a quadratic function, we see that a little bit better in the screen that we had before. You can see it here actually. You have a squared input, a input to the first, and a constant term. And I was going to write 3 decimals on everything. I don't like that when I only have 2 zeros, because that would mean only one significant figure. So I'm going to go a little bit deeper on that quadratic one, and I think I'll just go ahead and use 4. So 0.0018 times the input squared. It's plus and a minus, so I'll just write a minus. 0.0419 times t to the first. It's an 8, but followed by a 9, so I'll round up. And then that was times x, and then plus 0.5607. I did put more decimals on this just because I didn't like how many significant figures I was going to have here. To tell you the truth, when I go to do predictions, I'm going to use these stored functions, and so that'll give me more precision behind here anyways. And then finally the exponential function, which I expect is going to be the best one. What would that be like? So let's scroll down and see that one. So the number out front would be 0.1406, and then that would be times the base, which is 1.0649 raised to the t. So there's the linear model, mx plus b, the quadratic model, ax squared plus bx plus c, and an exponential model, a times b to the t. And then the reason that they're asking us to do all 3 is so that we could graph it and think about which one fits better. So there's the line. Here comes the parabola a little better because it's curving. And then here comes the exponential a little better still because it's curving, but shows curving steady growth, which is more likely for the cost of these Super Bowl commercials. Alright, let me move this aside now and see how we're doing on our questions. So find the linear regression, L, did that. Find the quadratic regression, Q, did that one, and the exponential regression, E. So there's all 3. And again, I personally find it inappropriate to do all 3 of them. I think what makes the most sense is to look at the graph, notice it's curving and that it's steady increasing growth, and go with exponential because of that. but on my math lab they're going to ask you to do all three, so I wanted you to see how that's done. And now they want us to think about which one is the best fitting model, and they're going to do that by focusing their attention on 1967, and we can do that, and I'll show you how. But again, I think that the best fit was E of t, and that's just by looking at it, that the linear one doesn't seem to fit as closely to the points. The quadratic and the exponential both curve and do a pretty good job of fitting, but the quadratic before this year was going back up, which doesn't make sense to me, so I'd rather see the steady growth out of the exponential. So that's how I would choose which one is the best. I'd say the exponential is the best because it's just the best fit to the scatter plot. But let's go ahead and look at their process for trying to decide which one's the best. So use these three functions L, Q, and E to estimate the cost of a 30-second ad during Super Bowl I in 1967. And then the actual cost was $200,000. Which one did the best job? So what I want to do there is think about, all right, 1967, to get T, I want to subtract out the starting year, and we're doing T years since 1960. So 1967 minus 1960 would be an input of T equals 7. And I'd want it, for these three different functions, see what is L of 7, what is Q of 7, and what is E of 7. And I could just put 7 into each one of these. In fact, it's not a bad way to go, but I did round every one of these equations, and that does bring in a little bit of error. So another way that I can plug into those, or have the calculator plug into those kind of automatically, something I have shown you before, is to use the trace and then have it evaluate the function for you. So I'm in here where I have all the plots going, so I'm going to hit trace and look at where I am. So right now it's on the plot, so I'll arrow down. That puts me on Y1. When I am on a specific function, I can move around and get X and Y values, but while I'm doing that, I could also just type an input like 7, and if I press enter, it'll tell me what the Y value is for that. So for the linear model, let me go ahead and swap these around. For the linear model, I'm getting a Y value of negative 0.352. And then let's see what happens if I go with some of the other models. What if I go with quadratic? So I'm going to go back to trace, get onto the second graph, which is the one with the x squared on it, and while I'm on there I could trace around to find values, but I can also just type that 7 in and press enter, and it will plug that in. So when I do that, when I put 7 and enter, it's plugging a 7 here and there and evaluating this, but not with just a few decimals like I have, but with a bunch of decimals like we saw in the y equals menu. And when I do that, for the quadratic function, I get an output of approximately 0.357. And then finally for the exponential, let me hit trace again and switch over to Y3, which is my exponential graph. Enter in the 7, press enter, and it'll plug into that one. And I get about 218 for that. So if I think about, alright, so what is it predicting? It's predicting with a linear model that in the year of the first Super Bowl, a commercial would have cost negative. Now these are all in millions of dollars, so I have to multiply times $1 million. And that's going to move the decimal over 6 spots. So this would be negative $352,000 roughly. This one, and negative, right? So that doesn't make any sense. They're saying that in that first Super Bowl year, if you wanted to run a commercial, you could, and the network would pay you this much money for the privilege of getting to air your commercial. So even if the Super Bowl, they didn't know if it was going to be popular or not yet, there's no way they were paying people to put their ads on. It was going to be the other way around. So that doesn't make any sense. And then we multiply this one by $1 million, we get $357,000, so that's at least reasonable because it's a positive amount of money. But they say up here that what it actually was $200,000, so that's a pretty big difference. We're predicting almost twice as much as it really cost. But if you look at the exponential one, you get $218,000. And so that one has the least amount of error. It's not perfect, but it's within $18,000. This one was off by almost double, and this one didn't make any sense. It came out negative. So they're having us do that just as an argument for the idea that this seems to be the best fit. What I don't like about that is they're making it sound like you should just put all your focus on that 1 year and that decides it. It is nice to look at that and see that you get the best estimate there, but it really should be more overall about all the data, which one's the best fit. And I think the exponential still wins there, and I would just do that based on the visual with all the graphs on my screen at once. Alright, when we turn the page, we'll go ahead and look at it a little bit more with this. Alright, moving on to part C, we found our equations and we have kind of decided that the exponential is the best fit, but they want us to continue examining that a little bit and looking at the different key features of each of these functions. So they want us to find the slope of the linear function, the vertex of the quadratic function, and to find the base of the exponential and describe what each of those means in the situation. To us, the most important are the slope and the base. The vertex is not as important because we didn't cover quadratics, but I can't skip that in my math lab, so I'm going to show you how to answer that for this one as well, but don't worry about that for tests. Alright, so for the slope of L, if I pull the equations in that we did on the previous page, for L we had a slope of 0.069t, and I would argue that the slope would be change in output, which was cost, divided by change in input, which was year. And then we had 0.069 for our slope, so I'll put that over 1. And then I'm going to start thinking about what that means. So the cost was in millions of dollars, so that's 0.069 times $1 million. And then the years, that's measured in year. So I would multiply through by that 100,000, and that would move the decimal over 6 spots. I'm sorry, multiply by the million, which moved the decimal over 6 spots. And I'd put the dollar sign out front, so that becomes 69,000, and then over 1 year. So I would argue then that the interpretation is that for each additional year that goes by, the cost of a Super Bowl commercial is increasing by about $69,000. So the cost of the Super Bowl ad, I'll say, increases by about $69,000. So with that one, we're saying that the cost is increasing at a constant rate and it's going up $69,000 every year. If that was true, we would see a linear pattern to the data. And I just want to remind you, if we look back at the graph, and I'm going to turn off each of those equations for a moment and just look at the data. If the data was linear, that would be true. The data seems to be curving, so I don't know if that's the best model for this. Let me go ahead and move to the base, because slope and base are the two that we really care about. So going to the exponential model, the base on that one, if I pull in the equation again from before, the base was 1.0649. So let me go ahead and write that down. The base was 1.0649. And you might remember from what we did with percentages that if you're multiplying by 1.069, the job of the 1 is just to maintain what was there, and the extra beyond the 1 is the rate of growth as a percentage. So if I cover up that 1, I can see the growth rate of 0.0649% per year. So that's what I would do to interpret that. I would say the cost of Super Bowl ads is increasing exponentially at a rate of, now I'm going to again move this decimal over to, think of it as a percent, so 6.49% per year. And if you're thinking, well, what about the 1? Just again a reminder, that 1 is maintaining the cost from last year, and then the 0.0649 is adding on an extra 6.49% each year that goes by. So when you're thinking about the growth rate, you want to kind of cover up the 1, and whatever extra there is, that is the decimal form of the percent growth per year, per day, per hour, depending on what your units are for the input. In this case, it was years. I'll mention the vertex real quick, but I'm not going to write this one down. For one reason is because of space, and the other is that's just not really even something we're covering. But if I want to do the vertex, what I want to do is go turn on the quadratic function. So I'll turn that back on in here, and then I want to look at its graph. And the vertex of a parabola or quadratic equation is the low point. We change the window to go to the left a little bit. You'll be able to see that a little bit better. And again, this kind of shows why we don't really want to go with this model. We don't believe that the cost was decreasing, and then all of a sudden turned around. But the vertex would be this low spot on the curve. And we find that just like we would an intersection. We go into the calc menu, second, calc, and then I want to look for a minimum because that's the low spot on that parabola. And they're saying, is this the function you want to do that for? Yes. They're asking for a left boundary. So I'm going to move the little cursor here somewhere to the left of the low spot and press enter. And now it says what's the right boundary. So I'll press enter to move somewhere over to the right side of the low spot. And when I do that, it's going to search for the lowest spot anywhere in between there. And they asked me for a guess, so I'll just move over. It looks like the low spot's around 12 or so. And when I press enter, it'll lock in on the absolute lowest spot, which apparently is at 11.4. So the vertex, and here I'll squeeze that one in. For the quadratic function, the vertex is an input of about 11.4 and an output of 0.322. So if I was going to interpret that, 11 would be 11 years after 1960, so that would be like 1971. And I would estimate that the low point for Super Bowl ad revenue was in 1971, and that it was about $322,000 per year. Again, don't stress too much over this vertex on the quadratic. You do have to answer it on a MyMathLab question, but I wouldn't put it on test because we did skip the chapters on quadratic. So we do want to be good, though, at interpreting the slope and interpreting the base. That's where you should focus your attention as you're doing homework. Alright, let's go ahead and move on to the last couple questions where they're finally going to concede that the exponential function is the best one and ask us to focus on that. So in Super Bowl, let's see, what have we got here? It looks like 36 with the Roman numerals. In 2002, a 30-second ad cost $1.9 million, and that was the first decline in cost. So what they're saying is the Super Bowl ad cost has been going up, and then that year was the first time it ever went down. Use E to help estimate the total loss in revenue from ad slots during that Super Bowl, which was likely due to a poor economy. So what they're saying is in 2002 the economy was doing kind of bad, and so they didn't get as much money as they might have expected from the revenue on these Super Bowl ads. So if we want to think about, well, what should it have been if the economy had not gone bad, we can use our equation to try and model that. So there's two ways to do it. One would be to figure out the t. We'll have to do that no matter how we do it, I guess. So you'd subtract 1960 away from the year of interest, which is 2002, and you get 42. So that's our input. So I'm trying to find E of 42. And one way to do that would be to plug into my equation. So I'll just bring that equation back over so we can see both, hopefully. Let me see, I'll fold this up for you a little bit. So there was my equation. So E of t was approximately 0.1406 times 1.0649 raised to the t, so I could plug into that. 0.1406 times 1.0649 raised to the t, but RT is going to be 42. So I can go ahead and plug that in on the calculator. Let me exit out of the graph screen. So 0.1406 times 1.0649 raised to the 42nd power. So when I do that, I get about 1.972, and again that's in millions of dollars. So multiply by 1,000,000, we'll move the decimal over 6 spots, so that would be 1,972,000. And then since I rounded that off, I'll just put zeros right there. Well, that's one way to do it. When I do that, I'm using a rounded base raised to the 42. I don't like the idea of rounding and bringing in error and raising something to the 42nd power. So another way that I could do that I think would be more accurate would be to go into the y equals menu, turn off the parabola, and turn on the exponential function, graph it. So give that a second or two to come in, and go into trace mode. So trace, and I'm on the plot right now, so I'll arrow down onto the y3, which is my exponential. And when I'm tracing on that, like I showed you before, if you just type a number, that'll go into the input. So I'm using 42. And then I press enter, and that plugs that into the equation, but not the rounded version. And notice that you can see our rounding error coming into play here. When I do that on the calculator, I get 1.975. So if you use the rounded version, you get 1,972,000. If you use the version that was stored into y equals, which has a lot more decimals and digits on it, then we end up, whoops, we lost that. So let me go ahead and plug that back in real quick. We get 1.975 with rounding. So that's a difference of $3,000. So that's fairly substantial. And that's not a surprise that if you take something with an error and raise it to such a big power that the error would spread. So I would recommend that when you go to plug in, you use your stored versions of the equations instead of the rounded ones that you wrote down. As long as you showed me the work, I would accept either one, but generally it's going to be better if you use that one that has more accuracy, which is the one that's stored. Alright, so they wanted to know how much did it cost them that there's a poor economy. So let's use the 5 because that's more accurate. They expected to make 1,975,000. They actually made 1.9 million, so 1,900,000. And if you do the difference there, that would be $75,000. So I think you could argue that the economy cost them about $75,000 in ad revenue. Now that's for every single 30-second commercial, so add that up over the whole Super Bowl. They could have lost quite a bit of money that year due to the poor economy. Alright, let's go ahead and take a look at one final part here. Use E, which is our exponential function, to predict the cost of a 30-second ad during the 2014 Super Bowl. So first of all, I want to figure out T. So T would be 2014 minus 1960, which was our kind of clock year for this problem, and we subtract that, we get 54. So I'd want to do the same thing, do E of 54. But I just showed you that if I raise this rounded version to the 42nd, it brings in error. So even worse if you raise it to the 54th power. So I'm going to go ahead and just do this one using the stored version. So I'm already in the trace mode. I'm just going to move around again, just kind of reset that, and type in the 54, which has the effect of plugging a 54 right there in the equation, but in the more accurate equation. And I get 4.201, but again, that's in millions. So that's the units on this, and when I put that there and multiply through, moves it over 6 spots. So we would expect in the 2014 Super Bowl that ad revenue would have been about $4.2 million for every 30-second commercial. Pretty amazing amount of money to try and get your point across in 30 seconds. Alright, so let me just point out a few things on this. One, we need to know how to interpret slope. That was from chapter 3 and 4 and 5. We need to know how to interpret the base. That's new for us now, so we're going to be doing a lot more of that these days. Interpreting the vertex is not very important for the quadratic because we skipped that chapter. It's just that I can't pull that part out of these problems in my math lab, so you're going to be asked to do that. And then the other big thing is when you're asked to make predictions, especially for an exponential with a big number plugged in, it's better to plug into a really accurate equation. So I would recommend that you store that equation into y1, y2, or y3, and then use the trace feature to get a really accurate estimate when you plug in, and to avoid the kind of rounding error we saw here when you try and plug into a rounded version. And then finally, this is their 4-step modeling process that they recommend, so I'll just go through that with you real quick. So if you're trying to find a model and use it to make estimates and predictions, the first thing you should do is create a scattergram of the data, and I highly agree with that. You want to look at a picture to see, is it straight, is it curving, does it actually dip, because then maybe a quadratic parabola type graph is perfect. And looking at the pattern of that data, decide whether it should be a line if it's roughly linear, a parabola if it's bending, or an exponential curve if it's bending. Usually the parabola would be if it was going to change directions, and we don't see that in too much of our real life data, so the exponential is often a better fit for us. Once you've looked at it and decided which one you think is best, you should find the equation of that model. I would suggest using regression. We've learned how to do most of these models by hand as well, but the regression is faster and more accurate. And then verify that your equation has a graph that comes close to the points in the scattergram. You can enter that into Y1 and let the calculator graph it, or better yet, when you're doing regression, you can store it into Y1 and then graph it. And if it doesn't seem like a good fit, maybe you made some calculation errors, well, we're letting the calculator do it, so that's unlikely. It says to use different points. That's if you're doing it by hand. We're using all the points when we do regression. And an alternative is to reconsider your choice of model. This is the one that might happen for us. If we draw it and it doesn't fit, well, then maybe we didn't make the best choice of line, parabola, or exponential, and we might try another one. But if your model does look like a good fit, then you can use that to draw conclusions, make estimates, and or make predictions. And what they're talking about there is stuff like this. Use the exponential to predict the cost of a 30-second commercial, so we figure out our input, we plug it in, and we get our estimate. All right, that wraps up Chapter 10.